So this is Abbe's famous diffraction experiment. What you see here is a model of a microscope. The microscope consists of a sample plane, of course. So here's our sample. We have then an objective that you find here. Here we have the pupil plane. Normally there's nothing there, but in this case we have a way to modify the pupil plane. So this way we can actually change what in the microscope, what information goes through the microscope and contributes to the image. And then here we have the tube lens. The tube lens will form an image on the screen over there. In addition to what a night microscope normally has, we have this little device here. And what it does, it takes some of the light, so a certain percentage is taken out of the beam, and then with this lens we form an image of the pupil plane right next to the other image. So that allows us to simultaneously see the image plane and the pupil plane. So what you see now on the screen is sort of a zoom into this pupil plane and the image plane here. On the top left, you can also see the modification device. So when I go with my fingers here, you see that I can now modify the pupil plane, and we can observe what happens to the image plane. So look at this. I'm closing the pupil plane aperture here, and you see that the image changes. For example, now we have only a few of these orders contributing to the image. Therefore, the image looks a lot blurrier. So let me go back. Here we have a relatively sharp image, and here we have a slightly blurrier image. When I then take away these orders, it is even more blurry. And when I finally have only the zero order transmitted, then all image information is gone. And I somehow imagine that this is maybe the, how to say, eureka moment when Abbe realized to form an image, you need interference of diffracted orders with the zero order. And what we're going to do now is we could do a couple of different modifications to analyze this concept a little bit further. So you see now what I put in here is a little device that you can see here that just lets pass one line of diffraction orders. In this case, we have no X diffraction orders, but we only have the Y diffraction orders, and only the central ones. So that means we have deleted all the X image information, and the blocks seem to be lines. Isn't that interesting that suddenly a two-dimensional object in the image becomes one-dimensional? You see fake information in some way, brightness where there was originally darkness in the sample. How is that possible? Well, because it's all about interference of diffraction orders. So this, of course, depends on when you rotate this. So, for example, if I go to a diagonal orientation, I get the interference along the diagonal, and you see a diagonal pattern. Even though the original block pattern that you saw there, the sample is actually just these transmitting square blocks. It doesn't seem to be in there, but of course, such a sample contains in its Fourier transform, if you want, also these diagonal orders. And if we just have them, all that is left is diagonal orientation. And if we go to the X direction, we can nicely now reconstruct only X information. So the next thing is I'm going to do the opposite. I'm blocking the central information here. Let me see to get that right. That's a bit better here. So we have no Y information left in the zero order. So there's basically the zero X, the zero X orders have been blocked, and only the higher X orders are present. And what you see now is something interesting, that the blocks seem to be subdivided, and we have basically twice as many blocks as we had before along the X direction. And this is called a dark field imaging mode. We are seeing just the edges, and there's twice as many edges in the sample as there is blocks before. So finally, I'm going back to the original orientation. So you see here that we have again this nice aperture, which we can close and delete the information. And what Abbe asked then is how many orders do you need to see image information? So for example, the fundamental one seems to be this one. Here we lost all the information. Here we can see something, but we still have both sides. And is that needed, is the question. And it turns out it's not really needed. Let me show that to you, because I can now change the area that I let through. And you see, for example, now I've deleted that order. There's still some information visible. And I can also delete the other order by moving it slightly sideways. I thought I can. Okay, now. So you see that actually to get the fundamental mode of this two-dimensional grating, I only need interference of 3 different orders. And this led that Abbe to conclude that that the resolution really depends on what distance of the orders you can let through. And with that, he came up with the famous Abbe equation of resolution.